Welcome to today's problem walkthrough. In this session, we'll be tackling the problem number 691, stickers to spell word. This problem is a great exercise to enhance your problem-solving skills, as it challenges you to think creatively about optimizing combinations and leveraging dynamic programming techniques. Let's dive in and explore how to approach this step by step. In this problem, you're given a list of stickers, where each sticker is a string made up of lowercase English letters, and a target word that you want to construct. The goal is to determine the minimum number of stickers required to form the target word. You can cut out individual letters from any of the stickers and rearrange them to spell the target. Importantly, each sticker can be reused as many times as needed. However, if it's impossible to construct the target using the given stickers, you'll return -1. The input consists of the list of stickers and the target word. The output will be an integer representing the minimum number of stickers required or -1 if the target cannot be formed. Let's look at some concrete examples to better understand the problem. In the first example, the stickers are with example and science, and the target word is the hat. To form the target, you can use 3 stickers. The first sticker with contributes the letters T, H, and I, the second sticker example provides the letters E and A, and the third sticker science gives the remaining T and H. Together, these 3 stickers cover all the letters needed to spell the hat, so the output is 3. In another example, the stickers are notice and possible, and the target is basic. Here, it's impossible to form the target because the stickers don't contain enough of the required letters. In this case, the output is -1. Now, consider the third example where the stickers are these: guess, about, garden, and him, and the target word is Adam. To form the target, you can use 2 stickers. The first sticker, these, provides the letter T and also has an E that we don't need in this case. The second sticker, about, contributes the letters A and M, which completes the target word. Since only 2 stickers are needed, the output here is 2. Finally, let's review the constraints and edge cases for this problem. The constraints specify that the number of stickers can range from 1 to 50, and each sticker has a length between 1 and 10 characters. The target word's length will be between 1 and 15 characters. Both the stickers and the target consist of lowercase English letters. Some important edge cases to consider include situations where the target is empty, in which case no stickers are needed and the output is 0. If the stickers list contains duplicates, those duplicates don't impact the solution since they're redundant. Additionally, if the target contains a letter that doesn't appear in any of the stickers, it's impossible to form the target, so the output should be -1. Small inputs, such as when the target requires repetitive use of a single letter, will test how well the solution handles these scenarios. To solve the problem of determining the minimum number of stickers required to form a given target word, let's first consider a brute force approach. The intuition here is straightforward. We try all possible combinations of stickers, subtracting the characters each sticker contributes from the target, and recursively calculate the number of stickers needed for the remaining portion of the target. While simple in concept, this approach quickly becomes computationally infeasible due to the sheer number of combinations that need to be explored. The time complexity is exponential, and the main limitation lies in its inefficiency. This inefficiency arises because the approach repeatedly solves overlapping subproblems, leading to a combinatorial explosion in runtime. It's clear that such an approach is not practical for larger input sizes. Now, an alternative approach we might think of is to use dynamic programming with bit masking. Here, we represent the state of the target string as a bit mask, where each bit indicates whether a specific character in the target has been covered. This allows us to systematically try all possible ways to use stickers while updating the state of the target string. However, despite being an improvement over brute force, this approach still suffers from high complexity, especially as the target string length increases. It's more structured but still not efficient enough for our needs. Instead, the chosen strategy takes a more efficient route by combining greedy principles with frequency matching, implemented through depth-first search and memoization. The key observation is that the order of stickers doesn't matter. What's important is how effectively a sticker reduces the deficit in the target's character frequencies. To achieve this, we pre-process each sticker into a frequency map, essentially an array of 26 integers that represent the counts of each lowercase English letter. With this pre-processing done, we define a recursive function that systematically attempts to construct the target. The function evaluates each sticker based on how much it contributes to reducing the deficit and chooses the most impactful stickers. This recursive process is made efficient through memoization, where previously computed results for specific target states, represented as frequency maps, are stored and reused. By avoiding redundant computations, we significantly improve runtime. The steps involved are clear. First, convert the stickers into frequency maps. Second, define the recursive function that tries all stickers and reduces the remaining target deficit. And third, leverage memoization to ensure we don't resolve the same subproblems. This approach strikes a balance between simplicity and computational efficiency, making it an excellent candidate for solving the problem within practical constraints. The efficiency of this approach becomes clear when we examine the complexity. The time complexity is m*2 to the power of n, where n is the length of the target and m is the number of stickers. The space complexity is 2 to the power of n, which is used for memoization. The key insight that drives this efficiency is the frequency map of each sticker, which allows us to quickly assess how much a sticker contributes to reducing the deficit in the target. By focusing on the most impactful stickers and caching results for partially solved subproblems, we avoid redundant computations and achieve significant performance gains. Comparing this approach to the alternatives, the brute force method, though simple, is computationally prohibitive due to its exponential growth. The bitmask dynamic programming approach is more structured but still struggles with long targets because of its exponential scaling. The DFS with memoization strategy, on the other hand, combines recursion's flexibility with memoization's efficiency, making it the most practical and scalable solution. This strategy offers a clear advantage in balancing efficiency and problem constraints, ensuring that we minimize the number of stickers required to form the target string effectively. To approach the problem of determining the minimum number of stickers required to construct the target string, we start by understanding the key elements. We have a list of stickers, where each sticker is essentially a string of characters. The goal is to use these stickers, possibly multiple times and in any order, to form the target string. However, each sticker has a fixed set of characters it can contribute. This means it's important to carefully manage how we use the characters in the stickers to satisfy the character requirements of the target. To get started, we compute the frequency of each character in the target string. This helps us quantify exactly how many of each character we need. Similarly, we compute the frequency of characters for each sticker. By analyzing these frequencies, we can begin to assess which stickers are most useful for reducing the target string step by step. With the character frequencies prepared, we now define the core of the algorithm using a recursive function called minStickers. This function calculates the minimum number of stickers needed to form the current target string. The base case is straightforward: if the target string is empty, we don't need any stickers, so we return 0. For the main logic, we iterate through each sticker to evaluate its contribution to the target. A sticker contributes by reducing the frequency of characters in the target that it contains. We subtract these contributions from the target's frequency and then recursively call minStickers on the reduced target to solve the smaller subproblem. To ensure we're exploring all possibilities, we use backtracking. This involves trying each sticker, tracking the minimum number of stickers needed, and resetting the frequency counts after each attempt. Lastly, we optimize the recursion using memoization. By caching the results of previously solved target strings, we avoid redundant calculations, which drastically improves efficiency. When designing the algorithm, it's crucial to account for edge cases. For instance, there might be situations where no sticker contains any of the characters required for the target. In such cases, we return -1 or another indicator to signal that constructing the target is impossible. We also need to handle special cases like an empty target string, which, as mentioned earlier, requires 0 stickers. The key insight here is that solving this problem boils down to reducing the target string character by character until it becomes empty. Stickers act as tools for this reduction, and our challenge is to minimize their usage. Since each sticker reduces the target and leaves a smaller subproblem, the problem has a natural recursive structure. However, it's worth noting that a purely greedy approach, choosing the sticker that contributes the most characters at each step, may not always lead to the optimal solution. That's why we need to exhaustively try all combinations of stickers to ensure we find the minimum. Memoization plays a critical role in optimizing this algorithm. By storing the results of previously computed target strings, we avoid redundant calculations, which significantly reduces the time complexity. For example, if we've already calculated the minimum stickers needed for a specific subset of the target, we can simply retrieve that result instead of recomputing it. To implement this effectively, we use a dictionary or cache. The key in this dictionary could be the target string itself or, for better efficiency, a tuple representing the frequency of its characters. Alongside memoization, we rely on frequency counts to track the number of each character present in both the stickers and the target. This can be achieved using dictionaries or arrays, depending on the character set. For instance, if the target is apt, we can represent it as a frequency count of 1, B2, C1. This representation is fundamental for both calculating contributions and updating the target during recursion. The algorithm relies on several key operations to manage and reduce the target string efficiently. One of the main operations is subtracting frequencies. For a given sticker, we reduce the target's frequency based on the characters the sticker provides. For instance, if the target is apt and a sticker contains a B, the resulting target becomes BC after subtraction. Once the target is reduced, a recursive call is made to solve the subproblem for the smaller target. After exploring all stickers, we choose the one that minimizes the total stickers used, adding one to account for the current sticker. To avoid redundant calculations, we check the memoization cache before performing the computation. If the result for the current target is already cached, we return it immediately. This combination of subtraction, recursion, and memoization ensures the algorithm is both thorough and efficient. To make the algorithm even more efficient, we can incorporate additional optimizations. One such optimization is pruning useless stickers. Stickers that don't contribute any characters to the target can be discarded upfront, reducing unnecessary calculations. Another optimization involves representing the target as a tuple of character frequencies instead of a string. This not only simplifies memoization but also avoids redundant computations caused by identical targets being represented differently as strings. Additionally, we can implement early termination. If a sticker completely matches the target, we immediately return one, as no further stickers are needed. Finally, while the recursive approach is effective, it may lead to stack overflow for very large inputs. To address this, we can convert the recursion into an iterative dynamic programming solution. This avoids recursion depth issues and provides a more robust implementation suitable for larger problem sizes. Here, we begin by importing the necessary modules, namely counter from the collections module to handle character frequency counts, and ru_cache from functools to enable memoization for optimization. Then, we define a class solution and the function min_stickers, which takes two inputs, a list of stickers and the target word we want to spell. The first step is pre-processing the stickers. For each sticker, we create a counter object to calculate the frequency of each character in that sticker, and we store these frequency counts in a list called sticker_counts. Next, we convert the target string into a counter object called target_count, which will help us compare the frequency of characters in the target with those in the stickers. To narrow down our options, we filter out irrelevant stickers, those that do not contain any characters needed in the target. We do this using a list comprehension, ensuring that only stickers contributing to the target remain in our sticker_counts list. Finally, we define a helper function dp, which will recursively solve the problem using memoization. The base case is straightforward. If there are no characters left to match in the target, the function returns 0, as no stickers are needed. Now, within the helper function dp, we first convert the remaining string into a counter object called remain_count, which tracks the frequency of characters still to be matched. We initialize a variable min_stickers to infinity, which will keep track of the minimum number of stickers required. Next, we iterate over each sticker in our pre-processed sticker_counts. If a sticker does not contribute to the first character of the remaining string, we skip it, as it cannot help reduce the problem size for this step. For stickers that do contribute, we calculate the next remaining string after applying the current sticker. This involves iterating over each character in remain_count and determining how many characters are still unmatched after using the sticker. We build a new underscore remaining list containing these unmatched characters. Then, we call the DP function recursively with this updated remaining string, adding 1 to account for the current sticker used. We update min underscore stickers with the minimum value between its current value and the result of this recursive call. Finally, the DP function returns min underscore stickers, representing the minimum number of stickers needed for the given remaining string. We solve the problem for the target string by calling DP with the target as input. If the result is infinity, it means the target cannot be formed with the given stickers, so we return -1. Otherwise, we return the result, which is the minimum number of stickers required. Here, we start with the Java implementation of the solution. First, we import the necessary packages, such as java.util*, to work with collections. Then, we define the solution class and the main method minStickers. This method takes in an array of stickers and the target string we want to form. The first step is to pre-process the stickers into a list of frequency maps. Each map counts how many times each character appears in a specific sticker. For this, we iterate through each sticker and calculate its character frequencies, storing the results in a list of maps called sticker counts. Next, we implement memoization to optimize our solution and avoid redundant computations. The memo map stores the minimum number of stickers required for each unique target substring we encounter. We initialize it with an empty string mapped to 0, since no stickers are needed to form an empty target. Finally, we call a helper method to recursively determine the minimum stickers required, passing in the preprocessed sticker data, the target string, and the memoization map. In this part of the implementation, the helper method begins by checking if the target string is already in the memo. If it is, we simply return the stored result to avoid redundant calculations. Next, we calculate the frequency of each character in the current target string using a map called target count. This helps us determine the characters we still need to form the target. We then initialize a variable minStickers to hold the minimum number of stickers required, starting with the maximum possible value. The method proceeds to iterate over each sticker's character frequency map. If a sticker does not contribute to the first character of the target, it is skipped, as it won't help reduce the target. For stickers that do contribute, we calculate the remaining target string after using the sticker by subtracting the sticker's character counts from the target's counts. This is done by iterating through the target count map, and any leftover characters are added to a string builder to form the new target string. After constructing the new target, we make a recursive call to the helper method to determine the number of stickers required for this new target. If the recursive call returns a valid result, we update minStickers to the smaller value between its current value and 1 plus stickers used, or the additional 1 accounts for the current sticker. Finally, we handle the case where no valid solution is found for the current target by checking if minStickers remain set to its initial maximum value. If so, we store -1 in the memo for this target, indicating that it is impossible to form the target with the given stickers. Otherwise, we store the computed minStickers value in the memo. The method then returns the memoized result for the current target string. This completes the implementation, ensuring that the solution efficiently calculates the minimum number of stickers required to form the target string using recursion, memoization, and the pre-processing of sticker data. The use of memoization significantly reduces the computational overhead by avoiding redundant calculations for overlapping subproblems. To solve this problem, we first pre-process the stickers and the target. Each sticker is converted into a character frequency counter, which tells us how many times each character appears in that sticker. For example, the sticker with becomes a counter where W, I, T, and H each have a frequency of 1. Similarly, example and science are converted to their respective character counters. The target word, the, is also converted into a counter, which tells us that we need 1T, 1H, and 1E. Next, we filter the stickers to determine which ones contribute to the target. In this case, all the stickers are relevant because they each contain at least one character from the target. With pre-processing complete, we move to the main recursive function, called DP, which helps us determine the minimum number of stickers needed to construct the target. The first call is for the entire target, the. We start by trying the sticker with, which contains both T and H. After subtracting the characters provided by with, we are left with just E as the remaining target. This leads to a recursive call to solve for the new remaining target, E. In the recursive call for E, the remaining target is just the letter E, which has a frequency of 1. We try the sticker example, which provides this character. After using example, the remaining target becomes empty, meaning there are no more characters left to match. At this point, we hit the base case of our recursion, which returns 0 because no additional stickers are needed. Backtracking from this, we calculate the total stickers used so far. Using the sticker with initially, followed by example, gives a total of 2 stickers. Therefore, for the first example, the minimum number of stickers needed to spell the is 2. Now, let's analyze the second example where the stickers are a, B, and C, and the target is ABC. First, we pre-process the stickers and the target. Each sticker is converted into a character frequency counter, so a maps to A1, B2, B1, and C2, C1. The target ABC is also turned into a counter, which shows that we need 1A, 1B, and 1C. All the stickers are relevant here since they each contribute to the target. We then begin the recursive function by calling dp on ABC. The first sticker we try is A, which provides the character A. After subtracting this, the remaining target becomes BC. This triggers a recursive call to solve for the new remaining target, BC. In the recursive call for BC, the remaining letters are B and C. We try the sticker B, which removes the B completely, leaving C as the new remaining target. This leads to another recursive call for C. In this next recursive call, the target is reduced to just C. Using the sticker C, we remove the final character, leaving an empty target. At this point, we reach the base case and return 0 because no further stickers are required. Backtracking through our calculations, we find that it took 1 sticker for A, 1 sticker for B, and 1 sticker for C, resulting in a total of 3 stickers. Thus, the minimum number of stickers required for this example is 3. In the third example, the stickers are A, AB, and ABC, and the target is CBA. After pre-processing, each sticker is converted into a frequency counter. The sticker A becomes A1, AB becomes A1, B1, and ABC becomes A1, B1, C1. The target CBA is also turned into a counter, which shows that we need 1C, 1B, and 1A. All the stickers are relevant since each contributes to the target. We then call dp on the full target, CBA. The first sticker we try is ABC, which provides all the characters needed for the target. After using this sticker, the remaining target becomes empty. Since we've reached the base case, we return 0. With the recursive function fully resolved, we can conclude the result for the third example. Using just the sticker ABC was sufficient to completely cover the target CBA, so the minimum number of stickers required is 1. To evaluate the time complexity of this solution, we start by analyzing the pre-processing step. Here, each of the K stickers is converted into a counter object to count character frequencies. If the average length of a sticker is M, this pre-processing step takes K*M time to compute the frequency counts across all stickers. Next, we have the recursive function, dp, remaining, which is the core of the solution. Thanks to memoization, redundant calculations are avoided, and we only process each unique state once. The number of unique states corresponds to the possible subsets of characters in the target, which is bounded by 2 to the power of n, where n is the length of the target string. For each state, we iterate over all K stickers and compute the new remaining string by iterating through the characters in target. This computation, on average, takes n time. Therefore, for each state, the cost is K*n. When we combine the number of states, 2 to the power of n, with the per state cost K*n, the overall time complexity of this recursive solution becomes approximately 2 to the power of n times k times n. Now, let's consider the impact of memoization. By storing results for previously computed states, we ensure that each state is processed only once, significantly reducing redundant calculations. Shifting to space complexity, the pre-processing step involves creating counter objects for the K stickers. Since each counter uses space proportional to the number of lowercase English letters, this step requires K*26 space. The memoization table is another contributor to space usage. It stores results for up to 2 to the power of n states, and each state's remaining string is stored in O(n) space. This makes the total space used by the memoization table O2 to the power of n*n. Additionally, the recursive call stack depth is bounded by O(n), as each recursive call reduces the length of remaining. This adds an additional O(n) space requirement. When we combine these factors, the total space complexity becomes O2 to the power of n times n plus k times 26. To put this into perspective, it's helpful to compare the current approach with a naive solution. A brute force method would generate all possible subsets of stickers and check if they can form the target. This has an exponential time complexity of k to the power of n, where k is the number of stickers and n is the length of the target. In contrast, our recursive solution with memoization avoids redundant calculations by focusing only on valid states, reducing the time complexity to O2 to the power of n times k times n. While this is still exponential in the worst case, it's a significant improvement. Now, considering the best and worst cases, the best case scenario occurs when the target can be formed using just one sticker, allowing the recursion to terminate early with a time complexity of k*n. The worst-case scenario, however, arises when there's little overlap between stickers, requiring exploration of all possible subsets of the target, leading to the full O2 to the power of n times k times n complexity. Finally, let's break down the big O complexity mathematically. The term O2 to the power of n stems from the number of unique subsets of characters in the target. For each subset, we perform k*n operations, as iterating over k stickers and calculating new_remaining both contribute to this cost. Combining these factors gives us the overall time complexity of O2 to the power of n times k times n. To summarize, this recursive solution with memoization strikes a balance by mitigating the exponential growth of state space exploration with efficient caching. Although the worst-case time complexity remains exponential, the practical performance is vastly improved compared to a naive brute force approach. On the space complexity side, the exponential growth is predominantly due to the memoization table, but this trade-off is essential to achieve the optimization. When solving this problem, there are several common mistakes to watch out for. First, it's important to consider all stickers during each recursive call. Stickers can typically be reused multiple times to construct the target, so failing to account for this can lead to suboptimal solutions. Next, inefficiently updating the target string is another pitfall. Many implementations create new strings repeatedly, which can be computationally expensive, especially for longer targets. Instead, using a frequency array to track the remaining characters is much more efficient. Another key step is pre-computing the frequency arrays for stickers. Without this pre-processing, you may find yourself recalculating character counts repeatedly, which wastes time. Finally, many solutions fail to prune unnecessary paths. For example, if a sticker doesn't contribute any new characters to the current target, it should be skipped. Including such redundant paths only increases the search space and makes the solution slower. Edge cases are another critical aspect to handle. For instance, if the target string is empty, the result should be 0 because no stickers are needed. On the other hand, if no stickers can contribute any characters to the target, the result should be -1. Missing these cases can lead to entirely incorrect outputs. In terms of optimizing the solution, decomposing the target string into a frequency array is a crucial step. This simplifies comparing contributions from stickers and makes operations more manageable. Memoization is another powerful technique, as subproblems often repeat. By storing results for previously seen targets, you can avoid redundant calculations and speed up the solution. Be careful with greedy approaches, though. Strategies like always using the sticker that contributes the most characters can fail to find the minimum number of stickers required. Instead, leverage BFS or DFS intelligently. BFS is great for ensuring the shortest path is found first, while DFS with backtracking allows for efficient exploration of paths with pruning. Lastly, when discussing approaches, it's helpful to highlight trade-offs, such as the fact that BFS uses more memory than DFS but guarantees optimality. This problem also connects to several related problems on LeetCode, which can help deepen your understanding. For example, LeetCode 691, our primary problem, focuses on using subsets of strings to form a target. Similarly, LeetCode 139, word break, involves determining if a string can be segmented into dictionary words, which shares a subset construction approach. LeetCode 472, concatenated words, revolves around breaking down strings into components, which also requires careful string manipulation. Finally, LeetCode 1044, longest duplicate substring, highlights the importance of frequency manipulation and optimization techniques. By exploring these related problems, you can better understand the underlying patterns and strategies that are broadly applicable. There are several alternative approaches to solving this problem, each with its advantages and drawbacks. A brute force approach involves trying all combinations of stickers recursively. While simple to implement, this method is highly inefficient and impractical for larger inputs due to its exponential complexity. A more efficient method is DFS with memoization, where you explore all paths in a top-down manner while storing results for previously encountered targets. This eliminates redundant calculations and improves performance significantly. Another option is BFS with state compression, where the target string is treated as a state, typically represented by a frequency array. BFS systematically explores all possible states and ensures that the shortest solution is found first. However, it can be more memory-intensive than DFS. Lastly, there's the dynamic programming approach, which builds solutions iteratively from smaller targets to the full target. While less intuitive, it avoids recursion overhead and offers a similar complexity to DFS with memoization. Choosing the right approach depends on factors like input size and memory constraints. Great job making it to the end of this walkthrough. We covered the problem stickers to spell word, explored different approaches, and highlighted the importance of optimizing solutions. Keep practicing problems like these to build your problem-solving toolkit. Thanks for watching, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!